Hello students, in lecture number 8 we are going to discuss about the response of causal LTI systems. In last lecture we discussed about the convolution sum and how we can use convolution sum to determine the response of LTI system for any given input. Now we are going to discuss about the class of LTI system which is causal. When we are talking about the real-time applications of digital signal processing, the systems and the signals involved are always causal. Right? So when we apply or we want to determine the response of the system in real time, then the convolution sum can be further simplified. Now we have already discussed in previous lectures what causal systems are, so just a quick review and then we'll move to the actual topic. The causal systems are those systems whose output at any time depends upon the present and the past values of the input, and it does not depend on the future inputs. Right? And this is what happens in real time, that the inputs which have already been applied or the input which is currently being applied are known, and nobody knows what would be the future input. Right? So in other words, the output of the system at some time instant n, for example n equal to n naught, depends on the values of x of n for n less than or equal to n naught. So this is what the causal system is. Now the response of LTI system at any time instance, for example n equal to n naught, is given by the convolution sum formula, right? So y of n naught is equal to summation from minus infinity to infinity h of k and x of n naught minus k, where h of k is the unit impulse response of the system and x of n naught minus k is the shifted and folded version of input signal being applied as input to the system. Now you can see this summation formula is from minus infinity to infinity, so it includes the time intervals from minus infinity to 0 and from 0 to infinity. Right? So we can actually divide this summation into two set of terms, right? One term from minus infinity to minus 1 and another from 0 to plus infinity. Right? So let us divide this summation into two terms, right? So the one term would involve the values of input signal when n is less than or equal to n naught. Right? So when n is less than or equal to n naught, these are basically the present and the past value, and similarly other set is when n is greater than n naught. So when n is greater than n naught, this is basically the future value of x of n. Now we can rewrite the convolution sum into this form. We have broken the convolution sum into two parts. One part where value of k is from minus infinity to minus 1, and other part when k is 0 to infinity. Right. Now let us expand these two summations. So after expanding, we will get this equation. Right. So this is the part where the k value of k is from minus infinity to minus 1, and this one is the part where the value of k is varied from 0 to positive infinity. Now in this part, the value of k is first equal to minus 1, then minus 2, and then minus 3, and so on. It carries until when k is equal to minus infinity. Similarly, when this part is expanded, so first value of k is 0, then value of k is 1, and then value of k is 2, and so on until k is equal to infinity. Right. So now if you look at these two parts of the expanded versions of the summation, you can see that this part contains the value of input signal, which are actually future values. Right. For example, x of n naught plus 1 is the future value of x of n, and similarly x of n naught plus 2 is also the future value. Right. So all the values involved in this part of the summation are basically future values of input. Right. So this summation, this part of the convolution sum, depends on the future values of input signal. However, this part, you can see the values of input signal are only those values which are either present value like this one, or the delayed version, the past values. Right. So what would be the condition for this equation to be causal? Right. Of course, this equation would be causal either input signal future values are 0, or h of n is 0 when n is negative, or h of k is 0 when k is negative. Right. So we can say that the condition for causality for this equation is when h of n is 0 when n is less than 0, right, or h of k is 0 when k is less than 0. Right. So this we can now say that condition of causality is h of n is 0 when n is less than 0. Right. So when n is less than 0, the summation, this would be 0, right, because whatever the values of x of n naught minus k are, h of k would be 0 for negative values of k. Right. So this part would be 0, and now this equation, the convolution sum, would be simplified in this form, where k is equal to 0 to infinity h of k to x of n minus k, and this convolution in summation is a special case which can be applied to calculate the response of LTI system, which is also causal. So hence an LTI system is causal if impulse response is 0 for negative values of n. Right. Of course, for a causal system, the impulse response is always 0 when n is less than 0. Right. So now if x of n, the input signal, input sequence, is also causal, right, then the values of x of n would be equal to 0 when n is less than 0. Right. So we can further simplify the convolution sum in this form. Now instead of k equal to 0 to infinity, k is equal to 0 to n. Right. So here you can see, when as long as k is less than n, this would only involve the values of the input signal, which are either current value or the past value. Or, as you know, that the convolution is commutative, so we can also rewrite this equation in this form. In this equation, h of k is multiplied with the folded and shifted version of x of n, and here x of k is kept same as it is, and h of k is actually folded and shifted. So these two equations actually can be used to determine the response of causal LTI system when input is causal as well. And this is the case of the real-time system. Right. When we are dealing with the real-time systems, then obviously the input signal is also causal and the system is causal as well. Right. So we can use this formula, the simplified formula, instead of the one we used last slide, which is more general. Now let us solve this example, and in this example we have to compute the unit step response of the LTI system whose impulse response is given in this equation, and impulse response is h of n equal to a power n into u of n, and the magnitude of a is less than 1. So u of n here is the unit step function, and as you know, where magnitude of a is less than 1, so it is actually decreasing exponential function, and this impulse response is actually causal, right? Because a of n is multiplied with u of n, and we know u of n is equal to 1 when n is equal to 0 or n is less than 0, and it is equal to 0 when n is less than 0, right? So values of h of n are 0 when n is less than 0, and values of h of n are non-zero when n is equal to or greater than 0. So this impulse response represents a causal LTI system, right? And obviously we need to find out the unit step response of the system. Then unit step input itself is causal, right? Because unit steps values are 0 when n is less than 0, and it is equal to 1 when n is greater than or equal to 0. So both the input sequence and the impulse response of the system are causal. Therefore we can use the simplified formula of convolution sum to compute the response of the system, right? So as I told you, the input signal unit step is given by this equation and is shown in this figure. It is a causal sequence, right? Because values of samples are 0 when n is less than 0 here, and it is equal to 1 when n is equal to or greater than 1. And similarly the impulse response is 0 when n is less than 0, right? And it is equal to 1 plus a square plus a cube up to a power n when n is equal to or greater than 0, right? This is actually the same example that we solved in the last lecture, right, using the general equation of convolution sum, right? Now we are using the special case, and obviously the answer would be same, but the method of solving, so since both input and the systems are causal, we can use simplified convolution formula that we just draw in few slides back. So y of n is equal to k equal to 0 to n h of k into x of minus k. You can also use the other version of this formula, which is x of k into h of n minus k, right? Answer in either case should be same. So y of n equal to k equal to 0 to n h of k into x of minus k. Now substituting the values, and we know x of n minus k is equal to 1. It is a unit step function, right? Its value is 1 when value of index n or k is equal to 0 or greater than 0. So we can further simplify it in this form, right? So since x of n is equal to 1 for n greater than or equal to 0, so y of n would be simply equal to k equal to 0 to n a power k, and this can be written in this form, right? So if you want to know how this value is obtained by solving this, you can refer to the last lecture in which we solved how we got this equation from this equation. So that's it. That's the solution of this example, and you can compare this solution with the solution in the last lecture, and you can see this one is more simplified version of that. Now similar examples are given for your exercise, in which you have to compute the convolution of x of n into y of n. Now x of n is given by this equation, and h of n, the impulse response, is given by this equation. Both these signals are multiplied with unit step function. It means they are both causal. In both A and B, right? So in this case we have to assume A equal to B and then solve the same example when A is not equal to B. So that is end of the lecture number 8, and if you have any problem you can contact me using the email address given in the first slide, and also we can discuss if you have any queries in the online interactive session scheduled on coming Wednesday at 10:30 a.m. Thank you very much.